Welcome to Lecture 3. This is the first lecture in Section 1. You'll recall from earlier lectures that I've divided the course into 6 major sections based on those realms of physics. This first realm I'm calling Moving Thoughts, Newtonian Mechanics. So we'll be looking at the mechanical system that Newton put in place hundreds of years ago that still describes much of what happens in the world. My topic for Lecture 3 is how we describe motion. Now, students beginning introductory physics are not always as thrilled by this topic as they might be. So I want you to contemplate motion for a little bit. Think about things that move. And think about what would happen in the universe if things didn't move. Cars move, electrons move around the nuclei in atoms, air moves to make the wind, the ocean currents flow, the rivers move, the stars move around the galaxy. All these things move. You move, your body moves, animals move. If there were no motion, everything would just be frozen. It would be as if you had put your video on permanent pause. Motion is what makes everything happen. That's why we're excited about motion. That's why motion is important to study. We want to understand motion because if we understand motion, motion is what makes everything happen. Then we can predict what's going to happen in the future. We can engineer structures that will move in the ways we want them to. We can handle motion. We can understand motion. That's why we begin by describing motion. And in this lecture, we'll be describing motion without asking why motion occurs. Later, we'll get into the question, the why of motion, and we'll in fact find that that isn't quite the right question, but that's something for the future. For now, we're simply going to talk about how we describe motion, both in words and in mathematics. Now, I want to emphasize that motion involves 2 important concepts. It involves the concepts of space and time. Consequently, the unit system we're going to be using when we describe motion will be the SI unit system I talked about in Lecture 2, but only 2 of the units will be important to us. The unit of time, the second, and the unit of space, the meter. So those will be the units we'll be working with in this particular lecture. We will also see that those units become later on the key to understanding relativity, because relativity, when we get to the modern physics section, is about space and time and how our visions of those have changed. But for now, we're just going to talk about space and time measured in meters and seconds. And furthermore, in this lecture and the next one, we're going to start simple because we're going to restrict motion to motion along a single line. That is, I might walk forward along a straight line. I might walk back. I might change my direction, that is, by going forward or back. I might walk at different speeds, but I'm going to restrict myself to motion that is along a single straight line. That's called one-dimensional motion. That greatly simplifies the description of motion, and it means a lot of the difficulties, a lot of the misconceptions that arise in understanding motion aren't going to plague us here. So we're going to start simple and restrict ourselves to one-dimensional motion. Let me begin with a story. The story I want to talk about is a story about going out to get some ice cream. So here's the story. You start out at your house and you stroll to an ice cream stand that's 1.2 kilometers from your house. And you walk at a steady speed and you arrive in 20 minutes. It takes you 5 minutes to eat your ice cream, and then you head back at the same steady speed that you went out with. But halfway home you come across a construction project and you pause for 5 minutes to watch. And you arrive home 50 minutes after you left. So there's a story. Got a lot of words. It's also got some quantitative information. I told you how far you went. I told you how long you paused to eat your ice cream, how long you stopped to look at the construction project, and so on. So let's talk about that story in more detail because that story contains the seeds of all the concepts we need to understand motion. So here's some questions about the ice cream story. How far did you walk? How fast did you walk? What was your average speed for the entire trip? How fast and in what direction were you going when you were heading toward the ice cream stand? And what overall change in your position occurred on the entire trip? So those are some questions. Each of these questions talks to or speaks to another concept of motion. So let's look at those motion concepts. How far did you walk? That's a question about distance. How fast did you walk? Well, that's a question about speed. You could have answered those pretty obviously. What was your average speed for the entire trip? Well, that is going to introduce the concept of average speed. How fast and in what direction were you going? That's a little more subtle question because it's really asking 2 things. It's asking how fast were you going, and it's asking in what direction were you going. The concept of velocity contains both those ideas, namely speed and direction. So velocity is a slightly more subtle physics concept. And then the question is, what's the overall change in your position that occurred over the entire trip? Well, there's two concepts involved in that question. One is the concept of position, where you are, and the other is a more subtle concept of displacement. And we'll spend part of this lecture developing these concepts in more detail. So let's get a little bit quantitative with these concepts. So we'll take a look here on the big screen. Let's do some numbers on that ice cream story. So the question, how far did you walk? Well, you went 1.2 kilometers out, 1.2 kilometers back. That's a total of 2.4 kilometers. That's how far you walked. How fast did you walk? Well, on the way out, you went 1,200 meters, 1.2 kilometers. Took you 20 minutes. That's 1,200 seconds. Speed is distance per time. 1,200 meters per 1,200 seconds. That's a speed of 1 meter per second. What was your average speed for the entire trip? Well, that's a question we got to be a little more subtle about. You went 2,400 meters. That's the total distance you walked. And you did it in 50 minutes. 50 minutes is 3,000 seconds. A minute is 60 seconds. 50 times 60 is 3,000. That gives you an average speed of 0.8 meters per second. Why is the average speed less than the speed you were walking at? Because some of the time you were stopped. Do some more numbers. How fast and in what direction were you going on the way to the ice cream stand? Well, you were going at 1 meter per second. We already worked that out. That was your speed. But this is a question about velocity, speed, and direction. And your direction was toward the ice cream stand. Maybe it was north, maybe it was south, maybe it was the X direction, maybe it was the Y direction. But I know for sure it was toward the ice cream stand. And that specifies the answer to that question. What overall change in your position occurred during the entire trip? This is an important one to get right. And the answer is you ended up back where you started. There was no change whatsoever. Your displacement for the entire trip, therefore, is 0. Your position did not change. It doesn't matter that you walked to the ice cream stand and walked back and stopped and ate ice cream and did these other things. The important answer to that question is, what was the overall change in your position? There was no overall change in your position because you ended up right back where you started from. So here's a graph of position versus time, position in kilometers, from 0.2468, 1 kilometer, 1.2, 1.4. And here's the time up to the 50-minute time of the entire trip. So what happens on this ice cream trip? Well, first of all, we go out to the ice cream stand 1.2 kilometers from home, and it takes 20 minutes. So I've got a straight line showing position increasing at a steady rate during that 20 minutes. Then we're at the ice cream stand for 5 minutes eating our ice cream. So there we are. Our position isn't changing. We're still 1.2 kilometers from home. Then we begin to head back toward home. We're going at the same speed that we walked out with, that 1 meter per second, and that's reflected by the fact that this line, which is now sloping downward, indicating my position is decreasing again. I'm getting closer to home. We're going downward. The position is decreasing. That slope is the same as this slope, except it's in the opposite direction. It's downward instead of upward. Then we reach that construction site. We pause for another 5 minutes. We observe the construction. Again, our position isn't changing. And finally, back we go to home, and there we are 50 minutes later, right back where we started from at position 0. No displacement, and yet we've gone on this entire ice cream trip. Quite a bit has happened here, and this graph nicely displays in one pictorial way what happened to us on this ice cream trip. So let's use these results now to develop some concepts about motion. One concept we want is position, and we're going to use position in this lecture. We're going to use the variable x, the symbol x for position. X is going to stand for a number which describes where I am relative to some origin, to some place I describe as position 0, and that's completely arbitrary. And I want to emphasize that right off the bat because throughout physics, students often get confused about the origin. They think it's something special or important. It's just a human construct. The way we designate where we are is always in relation to some starting point, and we call that starting point the origin, and we designate it in this case of simple one-dimensional motion as x equals 0. And again, I emphasize that choice of where that origin is completely arbitrary. In the case of motion in one dimension, along a single line, positions can be thought of as lying along a number line, and position could be either positive, depending on whether I go one way from the origin, or negative, depending on if I go the other way from the origin. But the only way we can designate direction relative to the origin in one dimension is with positive or negative numbers to indicate which side of the origin we're on. So here's a number line that represents position, and I've put position 0 in the middle. That's the origin. And to the right are positive positions, 1 meter, 2 meter, 3 meter, 4 meter, 5 meters to the right of the origin. Minus 1 meter is 1 meter to the left of the origin. Minus 2 is 2 meters to the left, and so on. Displacement, this new physics concept, a more precise concept that's related to but not the same as distance. I'm going to designate it by delta x. Delta throughout physics means a change in something. So delta x means a change in x. X stands for position. So delta x, that's the capital Greek letter delta, stands for change in position. You start at some position x1, you end up at some position x2. In that case, your delta x is x2 minus x1. The delta x is simply a shorthand way of writing x2 minus x1, where x is my ending up position, x2, and x1 is my starting position. So let's look on this number line at some displacements. So here is a displacement that starts out at x equals 1 and ends up at x equals 4. x2 is 4. x1 is 1, 4 minus 1 is 3. That's a displacement of positive 3, positive because I'm ending up further to the right of the origin than I started out. And its size is 3. 4 minus 1 is 3. That's a displacement of 3 meters, positive 3 meters. Here's another situation in which I go from x equals minus 3 meters to x equals 0 meters. Now, that's also a displacement in the positive direction. 0 is bigger than minus 3. 0 minus a minus 3 is 3. So that's also a displacement of positive 3. Those two displacements are identical, at least in terms of specifying delta x, the displacement. If you want to describe the detailed trip involved in going from minus 3 to 0, well, yes, that's different than in going from 1 to 4. But displacement just captures the change in position, and that change is the same in both. It's positive 3 meters. On the other hand, what if I start at 2 meters and I go to the left toward minus 1 meters? Well, if I do that, I've also gone 3 meters, but I've gone 3 meters in the opposite direction, so that's a change, delta x, of minus 3 meters. That's the concept of change in position, delta x, and from that we're going to build the concept of velocity as the rate of change of position. But before we do, we want to look at the relationship in a little more detail of this displacement concept, this change in position, to the more familiar concept of distance. So I want to look at some everyday words and some physics words, just like we talked about way back in Lecture 2 when we were beginning to introduce the idea that physics words sometimes had to be more precise than everyday words. So here's the question. Distance and displacement, what do those things mean? What are they like? How are they different? Distance is about how much ground you've covered. How far have you actually moved? That's what distance is about. It's always a positive quantity. Its direction is irrelevant. It doesn't matter whether I walked to the ice cream stand and then walked back. All that adds up to distance. It's what an odometer would read, or if you had a pedometer when you were walking strapped to your waist, it's what they would read. They don't care which direction you were going. They just give the overall on-the-ground traveled. Displacement, as we just defined it, is a change in position. The endpoints are all that matter. It matters where you started, it matters where you ended, and the displacement is simply the difference in that case. The details of the motion between those endpoints are completely irrelevant. All that matters is the starting point and the ending point. That's enough to define your change in position, delta x. It can be positive or it can be negative, as we just saw in the example on that number line. And if we look at the ice cream trip, little graph of the ice cream trip again that we developed before, the distance we went was 2.4 kilometers. We went out to the ice cream stand, 1.2 kilometers from home. We came back another 1.2 kilometers. The distance we traversed was 2.4 kilometers, but the displacement delta x for that case was 0. So understanding the difference between those two words, the more everyday word distance and the more physicsy word displacement, is really important because we're going to use the displacement word, delta x, the change in position, to calculate velocities. So let's look again now at two concepts that are also fairly similar, speed and velocity. But again, one is a physics concept and one is a more everyday concept. Speed is distance per time. It's always a positive quantity. The direction of motion is irrelevant. You look at your speedometer in your car and it says I'm going 65 miles an hour, but it doesn't tell you whether you're going northeast, south, or west. Speed is just about how fast you're going. It may vary depending on time interval. Now I'm stuck in traffic and I'm only going 25 miles an hour, so the speed may vary depending on what time interval I'm interested in talking about. Speed is distance divided by time. Velocity is displacement per time. And it might sound like that's the same, but it isn't. Because as we just saw, displacement is a different idea that depends only on your starting point and your ending point. So if I wanted to write velocity mathematically, it would be v is delta x, the change in position, divided by delta t, the time interval involved in making that change in position. All that matters are the displacement delta x and the time interval delta t. The details of the motion, again, are irrelevant. It doesn't matter what happened between the starting time and the ending time, between the starting position and the ending position. All that matters is what the overall displacement is and the time involved in undergoing that overall displacement. It can be positive or it can be negative. As we saw before, we had positive displacements and negative displacements along that number line, and if the displacement is negative, then the velocity will also be negative, and that's telling you the direction of the velocity. And in this case of one-dimensional motion that we're dealing with in this lecture, that's either positive or negative. We'll get much richer when we get to 2- and 3-dimensional motion. Again, the velocity may vary depending on what time interval I choose to deal with. I want to look at a 1-hour interval. I look at where I was at the start of that hour and where I was at the end of the hour. If I look at a 10-minute interval, I look at where I was at the start of that interval, where I was at the end. The velocity may come out differently in those cases depending on exactly the details of my motion. And if we look at the ice cream trip now, here again is our small graph of the ice cream trip that we developed. Things get a little more complicated. On the way out, from 0 to 20 minutes, that's one time interval delta t, the speed was 1 meter per second, and the velocity was plus 1 meter per second because my displacement was in the positive direction. 25 minutes to 35 minutes, that time I started walking toward home and then ended up at the construction site, that interval of 10 minutes, I was going at 1 meter per second. That was my speed, but I was going back toward the origin. My position was getting less as measured from that origin, which was my home, and so my velocity was minus 1 meter per second. What about the whole first 35 minutes of the trip? Well, that's a little more subtle. How far did I go? Well, I walked 1.2 kilometers to the ice cream stand. Then I rested at the ice cream stand eating my ice cream. And then I walked halfway back home before I came to the construction site. That was another 600 meters or 0.6 kilometers. And so I went a total of 1,800 meters, 1.8 kilometers, in 35 minutes. 35 times 60 seconds, that's 2,100 seconds. That gives me a speed of 0.86 meters per second during that part of the trip. So my speed for that part of the trip, actually it's my average speed, was 0.86 meters per second. On the other hand, because I walked 600 meters back toward home, my displacement was only 600 meters. I ended up 600 meters from home. I started out at home. The whole thing took 2,100 seconds. 600 meters divided by 2,100 seconds is 0.29 meters per second. So my velocity and my speed are quite different. My average speed is 0.86 meters per second. My average velocity is only 0.29 meters per second. So those two concepts are quite different. So let's look in a little more detail about this distinction between velocity and speed, this distinction between average and what I'm going to call instantaneous values of these quantities. So here I have a graph which shows position of some object as a function of time t. And you'll notice the graph is kind of curvy. It isn't a nice straight line, and that indicates that the position is changing at different rates, and therefore there are probably different speeds and velocities involved. I've marked two times t1 and t2, and I've marked the time interval, delta t, near the graph itself, and I've marked the corresponding change in position, that is the corresponding displacement, delta x, and over that time interval, dividing delta x by delta t would give me the velocity. And I'm going to call that now the average velocity over that time interval. But you might want to ask a more detailed question. You might want to say, well, how fast was I moving right near the beginning of the interval? And if you look at the graph, it's a little steeper then, and that suggests maybe I was moving a little faster. How fast was I moving in the middle of the interval? How fast was I moving near the end? And I can answer those questions by making those two times, t1 and t2, at the ends of my time interval, by bringing them closer and closer and closer and closer together. I eventually bracket just a single instant of time, and at that point, the value I'm calculating for the velocity is what I call the instantaneous velocity. So the average speed over a time interval delta t is the total distance divided by the time. The average velocity is the displacement divided by the time, delta x over delta t. The instantaneous velocity is the result of taking that limit as delta t gets arbitrarily small. How small? Well, you just make it as small as you possibly can. You could work that out computationally if you want to do an actual measurement over some very small time, a second, a hundredth of a second, whatever it needs to be. If you get into the mathematics called calculus, calculus deals with those limits and how you get precisely to that limit of arbitrarily, essentially zero-sized time intervals. And what we get at that point is the instantaneous velocity, and it's defined at every instant of time. So I can then talk about velocity as a function of time. It may vary continuously with time, and it ends up being the slope of the position versus time graph. That's because velocity is the rate of change of position. Instantaneous speed, then, what's that? Well, that's simply defined as the magnitude of the instantaneous velocity. The plus and minus are irrelevant. I want to move on to the last of the motion concepts, which is acceleration. And acceleration is analogous to velocity. It's the rate of, analogous to velocity in the way that velocity is to position. Acceleration is the rate of change of velocity. So let's talk about acceleration. It's the rate of change of velocity. Mathematically, the average acceleration is delta v, the change in velocity, v2, my final velocity, minus v1, my initial velocity, divided by the time interval delta t. Any change in velocity, and I want to emphasize that, this is a point of big misconceptions among physics students, any change in velocity implies there's an acceleration. I could increase in speed, I could decrease in speed, that's also an acceleration. You might use the word deceleration, but I just prefer to call that an acceleration. It's just an acceleration in a different direction. And finally, a change in direction. And this is the key one. We're not going to deal with this one when we're talking one-dimensional motion, but when we get to 2 dimensions and 3 dimensions, a change in direction, even if the speed isn't changing, is also a change in velocity and implies an acceleration. And then we can define instantaneous acceleration the same way we defined instantaneous velocity, by taking the limit of arbitrarily small times delta t, and then the acceleration becomes the slope of the velocity versus time graph. What are the units of acceleration? Well, it's velocity per time, change in velocity per time, so it's meters per second in the SI system per second. And that can be written as meters per second squared, as I'll show you in a moment. It can also be written as miles per hour per second. When you say a car goes 0 to 60 in 10 seconds, you're talking about its capability of accelerating at a certain rate. Let's take a look at these units of acceleration. Acceleration is the rate of change of velocity. The units are velocity per time. That's meters per second, and I'm going to abbreviate that meters per second squared. Where does that come from? Seconds squared? Well, what's 8 divided by 2, parentheses, divided by 2? Well, that's 8 divided by 2 is 4 divided by 2, and that's 2. But I can also write that as 8 divided by 4, or 8 divided by 2 times 2, or 8 divided as 2 by 2 squared. And this is the same way with the units. Meters per second comes out to meters per second squared. So those are the units of acceleration. Meters per second squared. Meters divided by seconds times seconds, meters per second squared. Okay, let's take a graphical look now at these motion concepts that we've been developing. Position, velocity, acceleration. Velocity, the rate of change of position. Acceleration, the rate of change of velocity. And again, the values of these quantities aren't directly related. They're related as rates of change. If I'm going 60 miles an hour, that doesn't tell you anything about where I am or whether I'm speeding up or slowing down or going at a constant speed. The values aren't related. It's the rates of change that relate these three quantities. And they all may change continually with time. So here's a graph on which I'm going to graph position versus time, another graph where I'm going to graph velocity versus time, and a third one where I'm going to graph acceleration versus time. So here's a graph of the motion of some particular object. This tells a little story. It says the object started out at position 0. It got further and further away, sometime between 5 and 10 meters from where it started is the biggest position it got to, the greatest displacement from its original position, and then it started heading back, and at a little past 4 seconds, it got to its original position again. So that's a story about its position as a function of time. On this part of the trip, somewhere around between 1 and 2 seconds, the slope of the curve is designated by that orange line, and that's representative of the velocity at that point, and it's probably the largest velocity the object has, at least on this first part of the trip until it gets going steeply downward that way. A little while later, it's at its maximum position, the farthest it is away, and at that point, the velocity is 0. That's the point at which the velocity curve, if we plot a curve of velocity, which started out at 0 and then rose up and came back down, that's the point at which the velocity is 0. That's when the rate of change of position is 0. There's a place where the velocity is a maximum. At that point, the velocity instantaneously is at its peak value, and it's going to start down again. And so at that point, the velocity is instantaneously not changing, and the acceleration is therefore 0. So this particular case, the object starts out with a fairly big acceleration, and the acceleration goes steadily downward. Position, velocity, and acceleration. Now let's take a look at these things as they work in the real world by doing an experiment. So here we are with a real-world experiment which will illustrate the concepts of position and velocity. What I have here is a motion sensor. It's similar to the thing in your camera that tells how far away subjects are that you want to focus on. It sends out an ultrasound beam, bounces it back, determines the time it took that beam to travel, and on the basis of that calculates position. And after it calculates position, it can then figure out, using the process of delta x and delta t, it can also figure out the velocity, and the results of the experiment are going to show on the screen here on the graph you see. So I'm going to place the motion sensor in front of this chair, which will be our object that's going to tell a little story about its motion. And I'm going to ask Kat from the teaching company to come forward, and she's going to take this chair on a little trip, just like the trips we talked about to the ice cream stand or the trips we saw in those graphs. And the graph of position versus time will tell a story of how this thing moved, and then we'll look also at the velocity graph. So go ahead. Beautiful. Okay, so let's look at what we've got. So the red curve is position as a function of time. I set the device to start registering when the chair got 1 meter from the motion sensor. So here these red numbers are the vertical scale. They're the position. So it started out at 1 meter. The chair moved away from the motion sensor at a pretty steady rate. You can tell because the slope is pretty constant. Then Kat paused when she got the greatest distance away. She basically was at rest. The slope is horizontal. The velocity was 0 at that point. The position wasn't changing. And you can see that on the velocity curve. Here's the 0 mark of velocity, right there where my finger is. So right across there is 0 velocity. And indeed, right when the chair was the furthest distance away, when Kat paused, the velocity was 0. Earlier, the velocity was fairly steady. That's on this rising, almost constant slope. Then it started to decline as the curve bent around. It got to 0. And then it went negative as the chair began moving backwards. And on her way back, Kat paused. Again, the position wasn't changing with time. And at that point, the velocity again went to 0. It was negative beforehand. It was still going backwards. It went to 0. And then as she rushed the chair back to the end, it went rapidly negative again as the position went back toward where it had started out. So this is a beautiful example of the story of the position and velocity as functions of time in that experiment. Well, thank you, Kat. I appreciate your efforts. And let's just wrap up by pointing out that we've learned 3 important concepts of motion: position, its rate of change, velocity, and velocity's rate of change, acceleration, and they're related in that the slopes of the graphs give you the next quantity down in that line. They are not related in terms of their actual values. We'll be using these concepts again and again in our study of Newtonian mechanics.